Hello everyone, welcome to the course on architectural design of ICs. So, today we will see one new topic which is this timing analysis basics. Not only basics, we will also see the advanced features or advanced techniques what we use in timing analysis while we are basically doing or while we are basically designing one digital IC design. Why this timing analysis is very much important is that whenever we are designing complex digital design circuits, so at that time there must be million of nets, million of gates, millions of interconnecting paths. So, unless and until we are basically guarantees that every path or every of this, that means this interconnections or these gates or the connection from input to the outputs are perfectly working fine, unless and until we are guarantees that it is not perfect, that the at the time of, that means testing this process or this IC design, they may fail. So, that is why this timing analysis is one of the important topic or important aspects which we follow in every digital design, present day digital system design. So, that is why we will see today, we will see the this basics, how it is actually with what it starts, and then we will see some of the advanced features like clock domain crossing, what is that, and when one actually circuit may fail to work perfectly fine. So, that advanced things also we will see in the later on of this particular lecture series. Okay. So, let us start with the very first thing. In any sequential machine, we know that there are two type of circuit may be there, which is one of the logic is in every digital circuits there are two type of circuits. One is this combinational logic, another one is the sequential logic. So, whenever in digital IC, whenever we are having both of them together, that means we have some combinational logic or we can name that as a combo logic, and then it has passes through the series of registers. Now, every registers may be actually connected with the clock. If every clock is connected with the same clock, then we can say that okay, this is synchronous design. If actually the clocks are different for this different registers or different sequential elements, so at that time we can say that the design is asynchronous circuit. So, we will see this, that means techniques which will be applied for synchronous circuit as well as the techniques which will be applied for asynchronous circuit design. So, actually the stored in sequential circuit there are basically states, the input state or the output state or the next state, from which state to what state it will go. The states are basically stored in the registers. The registers may be flip flop or they may be latches, whereas the combinational logic basically computes the operations. That means, whether it will go to which state, whether that means whether it will go to, suppose if there are 3 states, whether it will go to S0 to S1 or S0 to S2, at what particular input if we give. So, at that time it will go to S0 or it will go to S1 or it will go to S3. So, something like that logic basically depends upon the combinational logic, which computes the next state as well as the output from the present state, depending on the what will be the value of the present inputs. So, after that, in every actually this sequential circuit, the main important factor is that the clock. Then the thing is that why clock? Basically, this clock provides the means to synchronize the circuit. So, synchronize means in digital circuit, synchronization means the operations should be performed at what particular instant I need. That means, every operation, if I say that okay, within this particular clock period or within this particular event, every circuit will start operation or it will start performing the corresponding delivering the outputs or it will capturing the inputs. So, it depends upon the operation or the event of the clock. So, that is why this clock is basically present in digital circuit to synchronize by allowing the events to happen at known timing boundaries, which we can sequence this event, particular events, and we can sequence these particular events depending on the corresponding combinational logic what we have for the particular design. And it basically greatly simplifies building of the state machine. So, as we know that there are two type of state machine, Mealy machines and as well as the that means Moore machines, and no need to worry about the variable delay through the combinational logic, where all the signals are basically delayed until the clock edge. So, what does it means is that suppose as in the previous slide we have seen that we have three different combinational logic and the registers are same, where they have been driven by the same clock. So, at that time the three different combinational logic, they may have three different delay. So, at that time it is not that though they have this combinational logic have variable delay or different delay from each other. So, but the operation will be synchronized only based on the clock edge. That means, the data will be delivered to the next stage depending on the event of clock edge only. Whatever is the delay of the circuit or delay of this combinational logic, that does not affect the corresponding performance of that particular circuit. So, this if we see this, actually here you see this is the example of one finite state machine and this is just one simple, that means the sequential circuit example. So, where you see that okay, you have this resistors and in between you have this combinational logic, which is the data flow part of this particular circuit. So, then how to calculate this period or the clock cycle time? So, what is this clock cycle time? Clock cycle time is determined by the delay through the combinational logic. Why? Because all the signals has to be arrived before the latching edge, and if the signals arrives too late, it waits until the next cycle. That means, at that particular cycles or at that particular clock edge it will miss, and then what will happen? Because of that, the synchronization and the sequential order will become incorrect. So, that means, if I that means delayed or the my input or from the which is coming from the that means combinational logic to the registers, if they are being delayed. So, at that time the data will be missed at that particular event, which I basically intend to do, but at that time it will totally mess up the synchronization and the sequential order of my following design. So, at that time how we can actually how we calculate the cycle time is that depends upon the propagation delay through the combinational logic plus the T overhead. What is the T overhead? T overhead is the that means the delay for the registers. In registers also there will be one delay which will be associated. It is not that the registers are delay free. So, the register itself contains some of the delay. So, that delay plus the combinational delay. So, both the delay basically defines the cycle time. So, if I actually as an example, if we consider that 3 gigahertz Pentium 4 at the time, the cycle time for this is that 333 picoseconds. So, and if we want to obtain smaller T cycle, so smaller T cycle means what? Basically, I can optimize, I can maximize the operating frequency. So, to actually obtain this T cycle minimum, we have to change the circuit's architecture. Okay. Then how we can do? So, one of the technique is pipelining. So, what is this pipelining? Pipelining means instead of for this data flow part, instead of that means continuing one long critical path, if we can split the critical path into several chunks. Okay. So, if we can that means define that this the combinational part, if we divide into several chunks, that means we are subdividing the main operation into several subtasks, and then we can put the that means registers to store the intermediate results, which basically allows two waves of data to coexist within the combinational logic. Okay. So, actually if we see the example here, suppose this is my registers, and registers in between I have this combinational logic, which is basically combination of two tasks, which is task A and task B. The total path delay for this combinational circuit, which is this propagation delay of this combinational logic, is then that means the t cycle time will be T P D, which is the delay for this that means combinational logic, plus this T overhead, which is the registers overhead or registers delay. So, why it will be register delay? Because the registers are basically delivered, actually it associated with clock to Q delay, that means from the clock input to the output pin. So, here it will start from this output of the register, which is the Q pin, which will be traversing, the data will be traversing from this output from this registers to the combinational logic, then the clock to Q delay. So, that is why it is only TPD plus T overhead of, that means the only delay of one register, not the delay of two registers. So, after that what I did, that means depending on the techniques of pipelining, if we divide the corresponding work or task of A and task of B into two different combinational circuit, and in between them if I place one resistors. So, at that time this will be the TPD 1, that means the propagation delay which will be associated with only clock A, and the propagation delay which will be associated with clock, that means task B. So, at that time what will be the, that means minimum cycle time, which will be the maximum of TPD 1 or TPD 2 plus T overhead. So, at that time I can minimize the cycle time, because now it is already this total TPD is now divided by 2. So, it is, if suppose this in this case if this is 4. So, at that time I can divide it into, that means same by 2 and 2, at that time it will be 2 plus, if the T overhead is 1. So, 2 plus 1 it will be 3, which initially it was like 4 plus 1 5. Okay. So, by this actually subdividing the data flow part or this combinational logic, we can, and then putting the, that means the extra registers in between, we can increase the corresponding maximum frequency, or we can minimize, or what in other aspects or other context I can say that we can minimize the corresponding critical, the cycle time. Now, at what particular extra cost? Now, as we have already put these registers in between these two. So, we have put some extra area with this technique of pipelining to achieve the gain in terms of speed. Okay. So, now again let us revisit the cycle time and the path delay. So, in this particular case, if we see that this is the clock and this is the data. So, data is basically now at this particular, that means this cross, that means whether when there is the cross, that means at that time the data are basically changing. When there is, that means only white color, that means at that time the data are not changing. So, if we, that means say that okay, this basically this flip flop, this is the two flip flops. So, when these two flip flops are connected with some of the combinational logic in between. So, at that time I actually, to avoid the violations, always we have to consider that at the clock edge the data must be stable, it will not change its value. So, here you see at every of this edge, clock edge, the data are basically fixed, it is not changing its value. So, that is why this cycle time cannot be smaller than the longest path delay, which is the T max. Okay. And then longest path delay is a function of this total gate and the wear delays, where these gate delays are basically depends on the number of logic levels. That means, as in this particular case you see there are two paths which is basically following. So, in this particular path I am having 1, 2, 3, 4 number of gate delays, whereas in this particular path 1, 2, 3, 4, 5. So, 5 number of gate delays. So, at that time, so this will come at this will be considered as the critical path which consider this T max, okay. And that means the cycle time should not be less than this T max. If this particular that means this cycle time that becomes lesser than that, then at that time the data at the time it will, if this happens at that time, this edge will actually, this edge will come at that time, this edge will come here where the data are basically changing. So, when this edge occurs where the data are changing, at that time it will not work perfectly fine. So, it will not validate that what data it has been captured. So, that is why it will be in the ambiguous state, or you can I can say that is will be in the metastable state. So, that is why we just avoid to do that. Okay. So, then while we are considering this cycle, that means this clock, at the time the two important actually things we have to consider. One thing is this setup time, another one is this hold time. So, what is this setup time? The setup time is that we need, that means before this clock edge appears, we need some times where the data should not be changed. That means, to recognize the data properly, we need sometimes before this clock edge occurs, which is known as the setup time. Okay. So, for every flip flops to correctly capture the data must be stable as of the time period of T setup, which appears before the clock arrives or the clock edge arrives. Okay. So, before this clock edge arrivals of this, the data must be stable for some times, which is known as the setup time. So, in this particular case, so at that time the setup, the cycle time should be T max plus T setup, then only this particular this logic will work perfectly fine, otherwise it may fail. Okay. So, then if we say that okay, what is this, if we are having this clock skew. So, when we will get clock skew, if these two particular resistors are basically connected to two different clock, it is not that the same clock is basically same clock is connected, or this clock, this will be like clock 1 and this will be clock 2, though they have connected with the same clock. Why? Because in clock network, in digital IC design, they put some buffers in the clock tree path. Okay. So, that means that the particular delay where this clock appears to this Q1, suppose this is the source pin. So, the path or length from this particular pin to the Q1, that is much more lesser than the path delay which associated with the clock pin of Q2. So, this difference between this delay of arrival of the clock basically creates the skew. Okay. So, depending on that clock skew, now you can see that okay, this is the clock 1, this is the, that means this clock 1 signal, whereas this clock 2 can be like they will be shifted by some of the time as they are coming a long path, that means after a long path it is arriving to the Q2. So, that is why this particular edge is not aligned to the clock 1, there basically there is some difference. So, this is basically nothing but the clock example of clock skew. So, at that time the cycle time, if there is a clock skew, so at that time the minimum cycle time requirement will be T max plus T setup plus T clock skew. So, unless and until we consider this skew part here which is present in the circuit, so at that time this particular circuit will not work. That means, at the time if this is only, if I consider if there is skew, but still if we consider only max and setup, t max and t setup. So, at that time the corresponding t value will sample the data at a very faster rate, but depending on this t skew it will not work perfectly fine. Okay. So, then again if we consider this, actually that we have already say actually consider the example of cycle time as t PD or t max plus this t overhead. Okay. But here that t overhead is nothing but this clock to Q delay. Clock to Q delay means this is the clock pin to the Q. If I consider actually at this particular edge, this is the output which is the input to this is the long path from input to the output. So, this is the combinational part, then the setup, that means the setup time requirement, then the skew requirement, and then the delay of this particular register, which is nothing but this clock to Q delay. So, this all these particular 4 terms, summation of them defines the final cycle time of my circuit. So, in digital circuits we have not actually in generic digital circuits we may not have considered all of this, but in digital IC design we have to consider each of these particular terms unless and until the circuit may not work after its fabrication. Okay. So, then again you consider, actually there is another path which is hold time. So, now what is hold time? Hold time is the data, that means after the clock edge appears, the data must be stable for some times to properly recognize that what the value the data contains, whether that data contains 0 or whether the data contains to 1 state. So, for that particular reason, to properly recognize the state of the data should not change for a, that means time period, particular time period after the clock edge occurs. So, setup times is the time requirement before the clock edge arrives, and that means hold time is the time requirement after the clock edge arrives to properly recognize the data. Okay. So, here you see hold time after the clock edge arrives, and it is basically determined by the delay of the shortest path in circuit and the clock skew. So, the T minimum is the T hold plus T skew. Okay. So, this is the minimum timing requirement, that before this if the data occurs or if the data appears, so at the time this particular circuit will not work perfectly fine. So, in this particular case the minimum path is this, basically this one, okay, where it has only passed this particular 3 logic levels. This is the shortest path. So, which comes with this T minimum computation. Okay. So, if I that means take the example of one single phase clock. So, at the time here you see this is the time requirement for the setup and this is the time requirement for the hold, and from this particular edge to the next edge is the cycle time. So, within this summation of these two particular, this hold time plus the setup time plus the hold time, the data should be remain on the same state, it should not be change its value within that particular time period. So, here you see here also the data should not be changed. So, in between of this the data may change because they will not be sampled to the register, though they have changed this value here for so many times, but only the data will be sampled to the registers, only what value it occurs at this particular edge, and the data will be sampled which is occurs at this particular edge. Okay. So, intermediate values will be just ignored. So, if we consider that depending on the equation, so the maximum delay of propagation delay of the combinational logic, that will be T cycle minus T setup minus T clock to Q minus T skew. Actually, just the previous example where T cycle is basically the T max plus T setup plus T clock to Q plus T skew. So, if the delay is too long, the data will be captured incorrectly. So, we will see one of the example then, and if this minimum TPD is basically the minimum propagation delay is that that means the equation is that it should be greater than T hold minus T clock to Q plus T skew. So, if the delay is too short at that time, the data cannot be recognized properly and it will skip one state. Okay. So, that is why this, if we consider this example of this TPD max violation. So, here you see we are having this one registers A here, registers B here, and in between we are having some combinational logic. So, this A is basically connected with inverted clock, whereas this register B is basically connected with a direct clock. So, this is not inverted clock, sorry, this is skewed clock bar. So, now here actually this clock, this clock is basically like this, and this clock bar as this that is skewed. So, it will be arrive after some times, okay, which is this is the amount of skew. So, now at I, this is the, that means output from registers A, which is basically changing at this particular edge. Okay. So, at this particular edge, depending on this clock bar, it is changing, the data is changing. So, but at this edge of the clock, which is the requirement of this register B, it is holding the previous value of I. So, it will hold that value up to the next edge. So, at the next stage only this updated I value, they will be captured and they will be delivered to the next clock cycles. So, that means though this particular values should be contained the output here at this, but it is not holding that particular value, it is missing the state and it is appearing at the next clock cycle edge. Okay. So, that is why this is the problem which can increase the cycle time. Okay. So, then the example of TPD mean, that means if the propagation delay is minimum, at that time what violation or what is the violation we will get. So, the same thing, same circuit where this register B is now connected with the skewed clock, whereas this clock is connected with the register A. So, at that time what will happen? This is the initial, that means the original clock, and this is the skewed clock. So, if the I is basically changing the data over here, depending on this output from this combinational logic, they will come at this particular edge, and as this comes at the edge where this skewed clock is basically changing, it is from 0 to 1. So, at that particular time, it is that output from this combinational logic changing its value. So, it will be basically creates the problem, or there will be the properly recognition of the data will be incorrect. Okay. So, that is why this the O arrives before the clock, before the rising of the clock, skewed clock causes the data to be latched. Okay. And by changing actually this to solve the problem of setup time violation, if we increase the clock time period, so at that time we can solve the problem. But here by changing the actually this frequency or changing the cycle time, these particular problems may not be solved. Okay. So, we have different technique to solve this setup time violation and the hold time violation. So, later on this particular actually series, we will see what are the how to solve these problems in details. So, thank you for today's